Hello again, everybody. Welcome back to a new screencast lecture. Today's topic is states of matter, liquid. Let's get started. First off, we need a definition for liquid. A liquid is defined as a state of matter that has indefinite shape. Consider the following. If I have an orange juice filled up in a glass box like this, and I pour the juice into a different shaped glass box, incredible animation here. Did the juice change shape? Well, it sure did. It changed shape from the square shape to now this angled shape. The liquid will change shape dependent upon the shape of the container. What about the amount of space that the juice occupies? Does that remain constant? If I start with 100 milliliters of orange juice in the square container on the left, then I pour all of the 100 milliliters of juice into the other container. Again, some great animation. What will happen to the amount of juice that I have now? How much juice will I have in the second container? Well, of course, there will be 100 milliliters in the other container, even though it looks different. Part of our definition for liquid is that liquids have a definite volume. This means that if I have 100 milliliters on the left, and then I pour it into the other shaped container on the right, the volume does not change if the size of the container changes. And you'll see that even though that this liquid level is lower than this liquid level, it's the same amount. This container is more narrow, so the liquid will rise up to a higher distance than in here. This is the same amount of liquid, definite volume. This next clip shows a 5-year-old exploring the Piaget liquid conservation task. This goes along with what I just said about having this liquid amount and this liquid amount. This one's higher, this one's not. However, it's still the same amount of liquid. We understand that the more narrow container, the liquid is going to rise to a higher level. Now, a 5-year-old, they don't necessarily have the cognitive ability to understand that. Let's take a look at this clip.
And he's 5.5 years old.
Hi.
And we're going to do an experiment with him. So, Ethan, can you look at the two glasses there? Which cup has more, this cup or this cup? Or are they both the same?
They're both the same.
Exactly. We're going to see what happens when we pour this cup into the cylinder. Now, what do you think? Which one has more, this or this? Or are they both the same?
This one.
This one has more?
Because it's bigger.
What happens when we put it in this cup?
They're both the same.
How did that happen?
You poured it back into this cup.
So when I pour it in the cylinder,
It's bigger.
now it's more?
Yeah.
But then when I pour it back in the cup,
They're both the same again.
how does it do that?
You poured it back in. You measured, you took some out, and popped it. They're both the same.
Wow. Okay.
So when we pour this cup into here,
What happens?
they're not the same.
How does it do that?
So when they're when one's empty, one's full, that doesn't make them the same.
Okay. Thanks, Ethan.
Here's a quick review from our lecture on solids. Do you remember what the particles in a solid look like and how do they behave? Particles in a solid are relatively close together and they vibrate in place. Particles in a solid do not have enough energy to change position. That's why they're a solid. They retain the same shape. How do the particles in a liquid behave? Let's take a closer look. Here we see the particles do not look the same as in a solid. Here we see the particles in a liquid are not as closely packed together as those in a solid. We also see that the particles in a liquid are at a higher energy level than a solid. They're not just vibrating in place. The particles in a liquid are able to move and change position. If we were to compare the energy levels of a solid and a liquid of the same substance, say like water, the solid has a certain amount of energy. The particles are relatively close together. They vibrate in place, but the key is they do not change position relative to one another. A liquid has a bit more energy. Particles in a liquid are a little further apart from each other, and most importantly, they are able to change position. The particles in the liquid are free to move and to change position relative to one another. That's not like a solid. Although the particles are free to move about and to change position relative to one another, the particles do have some restrictions. They are restricted to the surface of the liquid. The particles don't spread out to fill the whole container. So these liquid particles don't just start shooting up or floating around over here, shooting out of the container. They are restricted to the surface level of the liquid itself. In our previous lecture, we used an analogy to kind of describe the motion of particles in a solid. We described particles in a solid as kind of like students sitting in their desks. They're wiggling around in their seats. They are in motion. They can move because, as we know, particle theory says all matter is made of particles, all particles in motion. So here you see these kids are in motion. They're moving. They're vibrating. However, the key is they do not change position relative to one another. So this student is in this seat, this student is in that seat, and they stay in those seats. Particles in a liquid, they're going to have a slightly different motion. So students are free to get out of their seats and to walk around. So like, for example, if we talk about this student, let's say the student starts having enough energy, he's moving faster and faster. He actually has enough energy to, he actually has enough energy to break free and falls out of his desk and starts rolling around. He's now changing position relative to this student and to this student. And that would be more like a liquid. So each student is able to get up out of their seats and walk around. They change position relative to one another. We can see the effect of particles in a liquid changing position by putting a drop of food coloring in a tube filled with water. Let's check out this clip. This next clip is a model of particles in a liquid. Notice that all of the particles are not moving in the same direction or even at the same speed. Here you can see that in a drawing where you have this particle is moving. The longer line indicates that this particle is moving this direction and it's moving faster than this particle, which is moving in this direction and moving a little bit slower than this one. Now this one and this one are moving roughly in the same direction. This one is moving faster relative to this one, shown by the arrow being longer. Let's take a look at that clip. Let's take a look at some physical properties of matter in terms of a liquid. One of the properties that liquids have is something called viscosity. And viscosity is the resistance of a liquid to flow. This next clip that we're going to take a look at shows the speed of flow of two liquids of different viscosities. The one on the left, rubbing alcohol, the one on the right, corn syrup. Here's a classic commercial that I remember from back in the day, from back in the 80s. This is a Heinz ketchup commercial, and it's bragging that Heinz ketchup has high viscosity. Of course, they don't say that Heinz ketchup has high viscosity. They just say that it pours very slowly. Let's take a look.
Usual. Coming up. Mind passing the Heinz? Sure.
When you've got something this rich, this thick, why waste time with anything else? Heinz ketchup. The best things come to those who wait.
Here are some definitions that go along with viscosity. Well, first of all, high viscosity means that the liquid flows slowly. Some examples of high viscosity liquids that flow slowly would be honey, peanut butter, syrup. Low viscosity, on the other hand, means that it flows fast, it flows easy. Some examples of liquids that flow fast and easy would be water, rubbing alcohol. Another characteristic of liquids and viscosity is that as the liquid's temperature decreases, as the liquid gets colder, its viscosity normally is going to increase. So in other words, it's going to pour slower. So let's use honey for an example. That's a good example. As honey gets colder, it's going to pour much more slowly. And one of the things you might have to do sometimes with honey is actually heat it up. If it starts to crystallize, you heat it up, get it nice and warm, and then when you pour the honey, it pours much faster than it does when it's at room temperature. Try it. Here's a picture of a liquid called pitch. Pitch has the highest viscosity of natural liquids. It is 100 billion times more viscous than water. Here's a clip from the Mythbusters. You may be familiar with that show. What they do here is they have a myth where that if somebody swims in syrup, that they could swim just as fast or maybe even faster than a swimmer would swim in water. Even though that the syrup is thicker and is going to resist your swim more, you also should be able to push off harder on that syrup than you would be able to push off on water. Let's take a look. Property of liquids, and that would be surface tension. Surface tension causes the liquid to act as if it has a thin film stretched across its surface, almost like a skin. This next clip is going to be of a water strider in action. You may have seen a bug like this, where it's standing on the water. It's standing on the surface tension. You can see that the water surface is actually even dented in here where the water strider's legs are touching. It's pretty neat to see these little critters zip around on the water surface. Surface tension is what allows water droplets to form. Water droplets will stick to one another and build up and build up and make larger water droplets. Surface tension is the interactive attraction between the water molecules themselves. So this molecule and this molecule are slightly attracted to one another. These water molecules have a slight attraction to one another, and that is what is able to make that skin that is on the outside of a water droplet. This next clip shows the effect of surface tension of water in zero gravity. Now, water is going to act kind of odd much differently than it does here on Earth. Here we see this astronaut on the International Space Station doing some fun experiments with something as simple as a water droplet.
Here in space, even the properties of a simple drop of water are quite fascinating. You notice here on the end of this straw, I have just a little droplet of water, and you'll find that water actually, as opposed to on Earth where gravity will pull it down towards the floor, of course here in 0G, surface tension takes over and the water tries to cling to itself and cling to whatever it might be near. And so in this case you can see I can stretch out that blob of water by just giving it a little bit of motion, or if I pull the straw away from the drop of water, I can probably, there you go, get the drop to suspend itself in the air. You'll notice that here between my fingers I have a drop of water that's separated, plus even an air bubble on the inside. And as I spread my fingers farther and farther apart, eventually the surface tension will be broken and the two pieces will separate. I can probably even get that air bubble out of there simply with a straw.
Well, guys, that's all we have for today. Hopefully you learned something. If you have any questions or comments, make sure you put them down in the comments section. If you like it, give me a thumbs up. If you didn't like it, give us a thumbs down. Obviously, we'd rather have thumbs up than thumbs down, but hey, I like your input. I like your feedback. See ya.